So yes, today I'll be talking about enhancing irrigation practices through audits and monitoring to better schedule irrigation. So I just want to begin with some resources. One of the resources that I've worked with some colleagues on recently is the updated Southern Nursery Association Best Management Practices Guide, which is it was published in 2013. And I also pulled the irrigation chapter off and put it in that resource chapter, Dropbox folder for you. But the main idea of irrigation management is to design to supply adequate and uniform application of water. The main goal is the right place, the right time, and the right amount. And with this, you'll manage to minimize excessive agrochemical leaching, hopefully saving you money by keeping agrochemicals on the ground where you apply them and nutrients in the container. Again, I just want to reiterate, it's really about the 3 R's, putting it in the right place, getting it to the container you want, applying it when the plant needs it and not before or after, and in the right amount so that there's not excessive leaching. Another resource we just finished in 2016 is the Advanced Irrigation Management for Container Grown Crop Ornamental Crop Production, and this is about a 16-page guide that goes through different calculations you can use at your nursery to increase efficiency, conduct the audits that we're talking about, and schedule irrigation. So that's one of the resources. Another resource that's come out at the same time was Amy Fulcher, who covers a lot of the same information, but she adds these really nice success stories or case studies that talk about successes in the industry and how they were used to reduce water or have other value-added benefits. One of my favorite resources is the Handbook of Technical Irrigation Information from Hunter Irrigation. This is a free download, and the first half of this book gives multiple calculations on pumps to infiltration rates on varying soil types, irrigation hydraulics, etc. It also has all of your friction loss characteristic charts for different pipes that you would use at your farm, and sometimes the polyethylenes that we use for drip or distribution of irrigation systems are hard to find, and they're in this system, and it can give you an idea of where you should be for flow versus pressure at varying different sizes when expanding or putting in new systems. The Rainbird system, many people use Rainbird. Sininger has similar things if you're using wobblers or other kinds of impact sprinklers. However, I like the Rainbirds because they also offer some more information that is in general on crop types, equivalency charts for size nozzles, root zone depths for field soils, etc., and can take you through a step-by-step calculation of how much water you should really be applying and at what rate that water should be applied at so you don't maximize runoff. So again, this is in the resource file. Sorry, I'm not used to the flipping. And all these resources I've gone through can be found at the link below as participant files by going browse to, or it's at bit.ly/can_irrigation, and you can see the different ones as well as a handout for today's talk. One last resource I want to talk about is an online resource that's very nice. Irrigation in the Pacific Northwest can be found at irrigation.wsu.edu. That's Washington State University. And this has a number of great calculators for both field and drip systems. I know you're probably not using a center pivot, though some growers do. But this is a great design calculators, etc. So please check out this website. It's a really nice resource that you can utilize. So let me begin the talk again, and I've organized this again by the right place, right time, right amount concept. So first we're going to start talking about putting it in the right place, placing the irrigation and getting as much as you can to the container. So first, it's about irrigation. How are you going to lay out your sprinklers? Is it a rectangular pattern, triangular pattern, or square pattern? All of these have advantages, and these are the major types. Notice that you have, these are all looking inside the zone or the bed, looking at full circle patterns, and all giving you different coverage and we'll talk about maximizing that coverage and these differences. Most nurseries that I see are more on a rectangular pattern or square pattern. Not many people use the triangular pattern, which can be beneficial in high wind situations because of the way the sprinklers overlap. So sprinkler trajectory or angle are both things that you should be thinking of. So how far does that sprinkler throw, and at what angle does it throw the water up? Lots of times we'll see people thinking that because they have a 5-foot crop growing there, they need a 7-foot riser. As you can see, the water does increase in height as it goes out from it, though a lot of it is on the bottom. So you don't want to go too excessively high, especially with impact sprinklers, because you maximize your wind drift and the wobble on the system, decreasing efficiency of that system. Also, the droplet size of your sprinklers is very important. It's based on the nozzle size you use and the pressure. So larger nozzle, lower pressure, bigger droplet size, that's going to be less affected by wind. Again, going back to sprinkler layout and arc. So each of these pictures shows you different ways that you can lay out the sprinklers. We have lots of times we'll have this incorrect sprinkler layout on the left, and if you look at the very bottom, it shows you how the water application pattern is. So we have irrigation depth that's applied over the distance from the heads if we're looking at the above square. So in this scenario, this is a lot of times how we irrigate, and we consider these areas on the edges to be roads, so we don't really care about it. But notice that you start getting inadequate irrigation even as you get just outside of the risers on the edge roads of this, and then it becomes extremely deficit or wasted water on the farther outside the zone. So this is an inefficient use of water. The other one would be the center one, where you put the 4 risers, and this increases your irrigation inefficiency, creating inadequate irrigation on the edges of them because there's no overlap. And then finally, the best correct sprinkler layout, which is not always liked because it's kind of hard to design with, is using half circle or part circle, quarter circle heads in the corners and on the edges, so that you get this very uniform application. Again, if you look at the graph at the bottom, it creates a very nice uniform application and also does not waste water within the roadways or in the walkways of the greenhouse. I mentioned head-to-head coverage earlier. It's very important that a nozzle shoots from head to head. That means that the radius that it shoots, a 30-foot head, the next head should be within 30 feet. Actually, in windy locations, you may even go 10% less than that. So for a 30-foot throw of a sprinkler head, you may drop that down to 25 feet if you know you're in a windy scenario, so that you maximize irrigation uniformity, because some of that will be lost to the wind and may not get full uniform. So these diagrams, A, B, and C on this, starting at the top, shows that if your heads are spaced too far out and you have 30-foot heads that are spaced 50 feet apart, you're going to have deficit irrigation in the middle, as shown with the water cans throughout this image. As you get them closer, we get more uniform, shown in picture B. But when we finally get the head coverage, we get that nice irrigation uniform. Think of these as containers on the ground. So if you want to add the water in A to be full, you're going to have to water twice as long or 3 times as long and overwater the edge groups. Whereas in C, the picture image C, you're going to be able to water at one consistent rate and get all of those containers full. One other concept that's really important when designing and implementing irrigation systems is match precipitation rate. It's a term that's used to calculate the amount of precipitation in a given area is uniform. So if you're going to use part circle, quarter circle, and full circle heads, what you need to do is make sure they have the same precipitation rate for that area. And you can look at this and think of it in flow rate for impact sprinklers, and ask your technical advisors from the irrigation companies you buy from. But 360 head is delivering 4 gallons per minute, or 1 gallon per minute to each piece of that pie you see. At 180 degrees or part circle, it's only delivering 2 gallons per minute, but it's still 1 gallon per minute per part of the circle. And finally, 90 degrees, It's just a 1 gallon per minute head. That way you're not overwatering in one region and underwatering in another region. So you want the same precipitation rate, and it's being visualized here as flow rate of the irrigation heads. Moving on to BMP, the best management practices, irrigation efficiency. Efficiency is getting the water that you deliver to the plant so it can be utilized for growth and delivering nutrients to that. Uniformity is when plants are irrigated in an area that will receive the same amount of water. That's getting the same amount of water to all the plants in the zone at the exact same time. A zone being an irrigation block or bench or what have you. That's the main goal. So for irrigation efficiency, the volume that's used by the plants for sprinkler irrigation systems such as solid set field production is about 70 or 80%. The soil helps us there because it helps distribute that moisture across the root zone. For container nurseries, we're down as low as 15% to 50% with an average of 20% water application efficiency. With micro-irrigation systems, we're up in the 80s for surface or spray systems because we're directly delivering that to the container. As I mentioned before, you're putting it where it's being utilized by the plant and not between the containers and having to process or pump it again. So what causes low efficient, poor irrigation system design? Improper installation of heads, as we've talked about, or poor management, excessive applications, running the system for way longer than its need. Irrigating with high evaporation demand or wind drift, so high wind times during your application. And then surface runoff or infiltration, leaching below the root zone, which goes back to the excessive application. So getting into a few terms, I wanted to explain how do we measure precipitation rate at a nursery or greenhouse system. This is a grid of containers or catch cans that have been put out that have straight walls. And so this is an example distribution of catch cans between 4 sprinkler heads in about a 1-hour location. And so we've measured the height or the precipitation rate in each one of these. And so in straight wall, you have to do a little more math if you use a cup that does not have straight walls. So straight walls is preferred, but it's an easy calculation. We share that in the publication that I mentioned before. But we calculate the inches of each of these, take the average, and we get how many inches per hour that we apply. 0.83 inches per hour is our precipitation rate. And we can also calculate the flow rate of the system using these same numbers. So this is just an illustration of how you can do this. This is a catch can system out from the BMP guide where they're irrigating and they're testing the irrigation uniformity across this system, and they'll go back after a normal irrigation run and do that. And then on the right side is a picture of a rain gauge just stuck in the gravel, or you could stick it in the container. And this will allow you to check your system to make sure that if you're having greater demand on it and not using variable speed pumps during the year, that you're still getting the same precipitation rate you want. It'll let you know how evaporation's impacting you and or wind. So it's a good way to check it. So have a few rain gauges around that you can stick out, and while your folks are driving around, they can dump them and make sure that they're giving the same amount of water, or if they're applying excessively. We use 2 things to measure uniformity, 2 coefficients. The Christian's coefficient of uniformity is the most complicated to calculate, but it gives you the average deviation or the uniformity across all of the cups that you put out and measure, and it's an absolute number. The one that is utilized a lot that's a little simpler to calculate is and gives you more information for scheduling is distribution uniformity, and it's the measure or the average of the lowest quarter of samples. So what it does is if you've got this grid, I put a star around each of the low samples that are below what is expected, and we take those 4 and get the average, and that's 0.68 basically, and divided by 0.83, and we get 81%. So we've lowered the irrigation uniformity based on this distribution uniformity. Again, these calculations and guides are in the resources I provided. So I worked with Rich Regan out in Oregon, and he came up with these numbers, and I find them to be pretty good. If you're using Christian's coefficient of uniformity or the distribution uniformity, you want to be in the mid 80s to know that you're evenly applying water to the system. If you start getting much below 80%, then you have a poor uniformity and you're probably considerably overwatering the system, you're considerably overwatering. If you think about a container nursery where you've only got 20 to 50% efficiency up front, and then you're having to overwater for a half an hour to make sure that all the containers are wet, you're really wasting and pumping some water that you could possibly be saving and possibly even retreating that water. So what causes poor uniformity? Inadequate or variable flow, too high or too low of operation pressure, inadequate selection of sprinklers or overlap that's inadequate. The wind effects we brought up multiple times, so you can go to your NRCS site and talk about wind breaks. And then change in system components with time, such as changes in your pump efficiency, your pressure regulators getting old or worn out or not being present. And then finally, grit going through your system that's impacting your nozzle size, or possibly calcium carbonate deposits or iron deposits that are impacting your nozzle size. I just want to bring this up. A quick way to, if you're designing, each of the irrigation companies, this is Syninger's, does have a distribution uniformity program that they can run for you. Lots of times if you're knowledgeable, they'll give you the system, and it is a starting point. You should still measure everything, but it gives you the ability to build out a system when expanding or building new systems and look at what the expected uniform distribution would be within that block or zone, and let you know how the precipitation rate looks like, and then you can actually calculate your runoff, expected pond sizes, etc., depending on what you're sizing those ponds for. Again, this is a starting point. Reality is not always the same as the software, but it gives you an idea of what that pattern will look like on the ground and give you more information. So you can see kind of this is a typical nursery zone where they're watering the roads, and they have pretty good uniformity because they back those heads to the edges of the road. The last thing I wanted to mention was scheduling coefficient, which is used heavily in agriculture and especially heavily in turf, but we do not seem to use it. If you know your distribution uniformity, this is very easy to calculate. So this allows you to adjust the length of an irrigation event. It accounts for those dry areas that we discussed earlier in distribution uniformity, and but it does not actually improve your application uniformity. It just makes sure everything gets the water it needs. So scheduling coefficient is the mean catch can volume by the average or lowest catch can volume, and you get a value of 1.2. So what you do is you just take the runtime you're using. If you're running for an hour, 50 minutes here in the example, you're going to multiply that by 1.2, and that way you know that it's going to be a 60-minute runtime so that everything gets that 0.82 inches of water that it needs. The other plants will receive a little more. That should not be 75% more water. They will receive more water. Sorry about that error. They will receive more water than the others, but it's a correction so that those plants in the driest zones do get the same irrigation that the others do. We talked about wear on nozzles. An easy way to check them is to get your drill bit set out and use the back of the drill bit for the same size as the nozzle and stick it in, and it should fit snugly. If it moves around or you notice boring on the edges, then it's probably a very good idea to change those nozzles. The other thing I've always noticed is, and I've worked at a few nurseries that where we're replacing nozzles and everyone has thrown the nozzles into the same bin regardless of their size, 5/30 seconds or etc., and they throw them in the same bin, so you're picking them out and you're just screwing in nozzles, but they're not all the same size. It's very important that these nozzles, very inexpensive to put these nozzles on, and keep them maintained for good irrigation uniformity. Also, if you don't have a variable speed pump, people have gotten resources and funding from state organizations to put pressure regulators under each of their impact sprinklers to regulate flow and pressure through those to get the right droplet size and ensure those heads are performing accurately. Dr. John Lee Cox always talks about a flow gauge, which you see in the left picture here. Amy Fulcher has been mentioning this as well. A flow gauge is an extremely telling device that can be a great advantage to you. Do you know how much water you're pushing? I mean, if you can just correlate time when you run an irrigation zone in one single flow gauge on your pump, you can figure out how much water is being thrown into an irrigation zone. And this is a good measure of flow rate to that zone, as well as the total gallons used. And it gives you an understanding of, well, that's got to be excessive, that has to be low. It gives you an idea of where you should be, and a little bit of record keeping on that lets you also know if something's changed, etc. The flow meter is also really good to detect any leaks in the system that may be slow and low, that are just constantly giving you off water, and let you know that system's leaking. On the right is a pitot tube, which is the wet way to measure your pressure at the furthest head from the pump in each zone. And you put this in, it's the same as works on an airplane, and you put it in line of the spray coming out of the nozzle, and as the water passes it, it gives you the pressure coming out of that nozzle. Excuse me. The other way you can do this, and I meant to add a picture, Dr. Anthony Bude has a nice setup where he actually just unscrews the nozzle itself from the impact sprinkler, plugs in a hose with a pressure, turns on the system, and he can see directly what the pressure is at there. That is a static pressure versus a dynamic pressure at that point, but they're both very intuitive to knowing how those nozzles are running. And if your head's supposed to be running at 40 and you're running at 70 psi, then you have smaller droplets, possibly further throw, and more wind effects. So onto the 3 R's. What's the right time to apply? So what time of day to apply irrigation? And many people are limited about this because you only have so much capacity. But if you're running drip in pot and pot, or you have the advantage of doing it, there can be some great benefits of being able to adjust your time. So researchers have looked at irrigating in the pre-dawn, which has been recommended in the past before sunrise, just in the AM, the PM, or all day, or throughout the day. So how do you irrigate throughout the day or multiple times in the AM and PM? Well, they came up with something called cyclic irrigation, which is if you know you're going to apply 60 minutes of irrigation for the day, then you would apply it in 3 20-minute bursts instead, with at least an hour, 30 minutes to an hour between the irrigation event. Now, some people have John may even talk about pulse irrigation, which is a step above this, but I'm going to stick with just cyclic irrigation. And we found that 2 to 3 irrigation, or 3 irrigation cycles is the best. What happens is that first 20-minute cycle starts to wet the substrate that's dried down, allows it to distribute laterally, and then you wait as that water continues to distribute, and some of that water gets used by the crop. The second irrigation cycle moves that wetting front further down and allows for more unsaturated flow to the sides. And finally, you get your third irrigation cycle, which you saturate that container, and you get about a 0.2 leaching fraction from, we'll go into leaching fraction, but you're going to get about 10 to 20% of the water that you applied to come out of the bottom of that container. And so you're distributing that water, so it's constantly being taken up through that period, and you're allowing it to not have preferential flow or channel run straight through that container, which we've shown recently in some of our research is quite prevalent in bark-based substrates and less prevalent in peat substrates. However, if peat starts to get hydrophobic, it can be just as prevalent. So this is research done on cotoneaster by Warren and Builder back in 2002, and they looked at plant growth as a function of dry weight shown on the y-axis with that pre-dawn AM p.m. all day on the x-axis. And they found that in the afternoon, you got the most considerable growth by wetting that plant continually, replacing that water, and ensuring the substrate stayed at a given moisture content. I'm sorry, I'm going to jump back real quick and make sure I put the caveat. Dr. Warren and Bilderbach's research at this time was done on micro-irrigation for cotoneaster, so this was being applied directly to the container where we saw the impact. This was also done in the southeast United States. We have repeated this research with Heather Stoven and some others out in Oregon. We saw less of an impact with the cool nights and lower day temperatures. So definitely, but in the south or in hot Midwest areas, this would be very relevant. Jumping ahead to overhead application. So impact sprinklers. This is cotoneaster dry weight done by Williamson, where we did pre-dawn, all day, and PM. And as you can see, the all day and the PM both were very effective in increasing the plant growth. That would be 3 cycles given throughout the day, or just in the afternoon at 12, 3, and 6 p.m. And he was able to increase growth in both of those by replacing the water and maintaining that substrate moisture content, allowing that water to distribute. One of the neat things that Carol Williamson saw was he looked at substrate temperature on 2 days in Raleigh, North Carolina, August 26th and August 27th. And so the y-axis is in degrees Celsius, and the blue line is the pre-dawn irrigation, the red line is the all-day irrigation, and then the green line is the PM, 12, 3, and 6. What's really neat is one of the reasons we believe that we saw so much benefit from it was that we saw these cooling effects. So they both start pre-dawn at the same temperature, and they rise in temperature about 10 degrees, but the first irrigation occurs for the PM and the all day, lowering that temperature about 5 degrees or so, and then it continues. And thereafter, each irrigation cycle, it further lowers the substrate temperature, keeping it from getting up there to 45 to 50 degrees Celsius. So it's actually cooling the system down. So as I mentioned before, you may not be able to do cyclic irrigation across your nursery, but think about some crops where you could really benefit from doing this. It may not help with wilt of hydrangea because that's a physiological response, but other plants that you believe substrate temperature may be impacting their response. One of the other really cool things about this research was that we found out that it took till 9 p.m. for the PM and all day to come together. And at 3 a.m. you finally had all 3 treatments, substrate temperatures, come back together around 25 degrees Celsius. So the majority of my talk then is on irrigation scheduling, which I'm getting to now. It's the right amount. Just simple things, thinking about growth stage or production phase. Is it the transplanter shift shown in the right container? Is it growing, shown in the bottom right container? Or do you have a saleable crop? And how do you irrigate these differently? Group plants by similar water use and increase irrigation efficiency. So putting the plants that you think have the same water use, you're more knowledgeable than us. One of the toughest things about nursery and greenhouse is the multiple taxa we grow. So grouping plants that are like in size, production phase, and water use are important. Also be considerate, this is a good reason to have uniform irrigation, uniform substrates as well, so that they hold the same amount of moisture and you don't have one thing that's a much drier substrate than the other. So putting like substrates together can be quite influential as well. Something that's not as thought of all the time is plant architecture. Do you have an umbrella plant or a vase plant shown on the right? The umbrella shown on the left and the vase plant shown on the right. And part of that research that Dr. Carol Williamson, not a doctor, but Carol Williamson was doing was looking at daily volume applied for cotoneaster, gardenia, and videx, and percentage capture. So the amount that he had to apply to maintain the same amount of leachate in those, which he was shooting for 0.2 leaching, as we talked about in cyclic irrigation, He actually had to continue to add water to the cotoneaster, which if you look at the picture down there, it's your umbrella. The Vitex, which is a vase, decreased throughout the season, whereas gardenia stayed quite level. The percentage capture shown in the right slide, and the y-axis is volume, over the 105 days of the study, you can see that the percent capture went up to 200% for gardenia and Vitex, whereas the umbrella-shaped plant cotoneaster was unable to funnel plant into it. What I'm speaking of is that we think of leaching fraction is based on this capture, and you can't have a 200% leaching fraction, but what the plant's doing is it's creating a vase that's wider than the container. So when I was giving you those efficiency numbers, those have always been based on the container surface area. But what we know is as the plant grows, we actually start to fill out that void space, and our irrigation efficiency is reaching and getting more efficient as we go. So we're decreasing that, or we're increasing that efficiency and increasing our capture to each container, and that's more sought after with gardenia or Vitex, which are vase-like plants. And what the implications of this is, even though cotoneaster and gardenia may be similar water users, I know they're not, but for the example, you would not want these in the same place because they're going to have a very different ability to capture water into that container system. Hope that was clear. We continue some of the plant architecture work at Bailey's with Dan Bailey, a graduate student at Oregon State University, where we are looking at prune plants versus unpruned plants, different canopy shapes, etc., and doing trying to understand better what this means to irrigation efficiency. What I thought was very interesting was he did, the graph is the height and width of the containers and the increase in irrigation capture. And what we found is that height matters as much as the width of the container. And if you think about it, your irrigation is not raining straight down on that container, but is coming at an angle. So we may have biased this data by the way they were spaced to some extent, but what we learned is that plants that had irregular up and downs on them were able to also capture water from the side because of the trajectory of that angle, the trajectory of those nozzles hitting them on the side and being able to funnel water down them as well. So if we look at increase in irrigation capture from unpruned to pruned plants, so another thing to think is if you go in and prune half a block, you're decreasing the irrigation capture down to 0.5 versus three times that of the unpruned plant of similar structure. So as soon as you prune them, they're much able to do. Now this is self-correcting in that sense that you've taken the leaves away from that plant and decreased evapotranspiration, but you should be considerate of that at different times of the year, and that it may be hard to keep some plants dry while keeping other plants wet. An easy way to schedule irrigation that I like is the bucket method. The maximum water holding capacity of any substrate's about 25 to 40% of available water. So if you put a container out of the same size you're growing on, put a plastic bag in it, if it's more than a third filled with water after an irrigation, you've watered too much in that day. So you can put these out and dump them, and you know how much you're watering. So you shouldn't be able to hold more than a third of that container should be full of water after an irrigation. So that's an easy measure. If you drive by and that is overflowing with water after one irrigation event, you know you have excessively applied water to that system. Leaching fraction is the volume leached divided by the volume applied. And so we measure that as an open bucket is the volume applied using a volume method, and the container in a bucket what leaches through the system. We have a nice extension. This is in the extension bulletin, and this is from an article, so you can see large containers that are being drip irrigated. You can use a milk jug and then put them in a pan where you can collect the leachate, or for large containers you can put them in buckets for overhead irrigation, as shown on the bottom, where you can nest them. Typically you can find buckets at Home Depot that work for different size containers. The other way to do this, where you won't get excess over 100% leaching fractions, is you can use the weight-based method, which you don't need cylinders or anything else, because 1 ml of water equals 1 gram of weight. So you just weigh the plant before the irrigation, weigh it on after irrigation, the weight difference is the volume of water applied, and then you weigh just the leachate that's been captured in the lower bucket and divide them, and you have your leaching fraction. We can use the leaching fraction data to actually adjust our irrigation. So if we want to calculate our new irrigation, we can use t, the small t, as time, and then our leaching fraction, target leaching fraction, minus our actual measured leaching fraction. So after 50 minutes, we have a leaching fraction of 0.55. Our target is 30. We can plug that in, and we should reduce our runtime by 12.5 minutes, giving us a 37.5-minute runtime instead, lowering that. It's hard to keep up with that. We suggest a target of 0.15 leaching fraction or 0.20. I would say start off a little bit higher than that until you get used to it, if you're adjusting your clock, etc. Leaching fraction is really nice. This is an example of cumulative water applied over leaching fraction, 0.1 versus 0.2 leaching fraction. So I went from having 10% of the water I applied leached out to 2% of the water I applied leached out. And just by decreasing it, I saved 7 gallons per container on that pad by decreasing the leaching fraction from 20% to 10% or 0.2 to 0.1. And this equates to about 90,000 gallons of water saved per growing acre while maintaining growth, and about 55,000 gallons less per growing acre being leached from the system that has to be retreated or carrying agrochemicals. Jane Stanley in 2014 presented that leaching fraction. They started implementing this with Dr. Yeager's help, and showed that they could reduce water savings by about 45%, and this equated to a savings both in fertilizer and herbicides So these are actual real numbers in which they've been able to reduce their water, their fertilizer, and their herbicides. Real quick, I just want to mention crop water use, where we have which is where people actually measure evapotranspiration and figure out actually how much the crop is water using. A bunch of scientists have worked in this arena: Dr. Yeager, Dr. Beeson in Florida, Tom Fernandez in Michigan, and Rich Regan in Oregon. So this is just a list of plants showing how much acre and inch of water they utilize in a day. And so he was able to break them up, with Buddleia being a very high water user versus Ditzia gracilis using very low amounts of water, so that you could start to be able to group these plants better and be able to replace the water as they actually use them and be informed about plants' water use. He also looked at deficit irrigation, so replacing the water used by the plant, but also reducing that volume periodically to grow plants under deficit irrigation for short periods of time to increase irrigation efficiency. And this is the results they came out with. The amount, this is the amount recovered based on 100% land use with number 3 containers, spaced 1.5 feet on center over a 4-month period up in Michigan. And so the treatments they had was the control, 100% daily water use, so they're putting back the exact amount of water that's used by that they measured in that previous graph. Then they alternate 100 by 75%, so they only give it 75% of the water it uses daily or every other day, and then they switch off to giving it only 75% of the water it needs on days 2 and 3 before it gives another 100% shot. And they were able to reduce the amount of water applied from 330,000 down to 182 with 100,000 gallons of water savings, and they were able to go down about 100 gallons acre of runoff as well, so less water needed to be treated. So do you need to water every day? Is there advantages to possibly drying out that day? I always like this because this is a simple solution to trying something that you can automatically every other day increase your irrigation efficiency by 25% without potentially seeing any negative effects. A quick picture of the plants they grew. The numbers represent their growth index. And so this is at the middle of the study, and at the end of the study, you have the control on the left, the 100% daily water use efficiency, deficit irrigation for 1 day and deficit irrigation for 2 days on the far right. And as you can see, there's very little effect until you start drying them out every other day. Now this is a cooler night environment. With our increasing night temperatures, you may not be able to see this, but you could still try to cut it down 20% every other day from your schedule. So go from 60 minutes to 45 minutes or 50 minutes, and see if you see any detrimental effect, and increase your efficiency and decrease your pump times. I just want to mention user-friendly. Dr. Yeager's created the CIRIG, or the Container Irrigation Management Program, which is an app that's used for Florida, and it actually, based on your plant's canopy, ET, etc., it helps calculate how much water you should irrigate. And so it calculates the run times based on your production and irrigation inputs, your irrigation application rate. It's currently available in Florida, but he's beginning to test it more widely, and it's currently being tested in 2 nurseries in Virginia, I believe. I'm not talking much about new technologies. I'm just giving you a quick overview. This is what John Lee Cox will be speaking about next week in detail, but there are new advanced technologies that can let you see stuff from your phone or your computer that can better help. Load cells are not commercially viable yet. That's where a lot of my research, and that's a gravimetric approach to measuring the weight of the container. Again, going back to the concept that 1 mil equals 1 gram, and that's shown with that rose on the left side. Capacitance probes, such as the decagon sensors, are very user-friendly and much more commercially available, and I believe that's what John will be talking about. But these do all provide very different they provide very similar readings, and you can see these diurnal water fluxes. We deployed this system at Bennett's Creek Nursery. This is the app that we used with PureSense, who is now owned by Jane. But as you can see, this is your phone or your computer screen, and each one of these green markers shows you how that container is doing. If it's blue, it's happy. Yellow, it needs water. It's drying out. Red, it needs water. And you can click on each one of them, and you can pick up and see. With most of these, we've always been worried as academics about how accurate they are for moisture content. But to be honest with you, what I learned in Oregon is it's not that important. You know what dry is, and you know what wet is. So if you look at the picture on the left, if you set your lower bound, which is the red zone, as I don't want to go drier than that, and the blue top is I don't want to go wetter than that, then that's your 2 points that you want to start with to start learning from, and then you'll tighten up those bounds as you go. And what's really nice about this, the blue line through here shows you how your moisture is. It shows it drying down, then you irrigate, then you leach, and the initial, that's that steep peak, and then you start to change moisture over time and dry down again. So you can see how well you're irrigating and what's happening with that water when you irrigate. One caveat, and I'm sure John will go into, Dr. Lee Cox will go into greater detail about this, but when using any of these devices, even load cells have issues with this, is that when you're thinking about it, know that your percent moisture in your container is a distribution within the profile. This is the height of the container of 16 centimeters. With moisture from 100 to 0. It's also visualized as a container on the right. So your percent moisture is 69% at the bottom, or 70%, where it's only 30% at the top. So where you place these probes or what you're measuring with a load cell varies considerably. So based on where you and what you want to do with those, you just need to be conscious about doing where you place these probes. In small containers, it's not that big of an issue. It becomes greater importance as you go to larger containers. The last 3 slides just for fields. I just wanted to bring water and nutrient management. Sam Doan shared these slides with us, and they're measuring soil moisture using a portable probe called the Diviner tube from Australia. And these are moisture graphs at 4, 8, 12, and 20 inches over the month of June in 2003. And they're looking at moisture flux in those different horizons of the soil. And as you can see at the 4 inches, you're getting all kinds of noise. You're drying out, you're wetting, you're drying out, you're wetting. But at 20 inches and 12 inches, you're staying quite stable. In their situation, they learned that they were getting hydraulic lift of water actually from the trees planted in the nursery, helping replace that surface water so that they didn't have to be so reactive to the 4 inches. So they were able to considerably reduce their water. I'm not sure of the number, but I think it was 50% or greater. And so what they found is this is a slide of their cumulative energy savings over the different years as they implemented this in 2003. And as you can see, they started saving up to 1 million kilowatts per hour by implementing this as they reduced their irrigation, letting the soil probes inform them and let them know that they also could replace water from the base as well as the top. And this is the cumulative financial savings from 0 to 100,000 over that same time period of 2003 to 2010. And so eventually they were able to save about $100,000 through that pump time. They were also able to better apply fertilizer through that drip tape throughout that period and be more efficient with nutrients. That completes my seminar. Thank you all. It's always hard to talk to an audience that you can't see, and I hope you're following along. I know some of it's math-based, but I really enjoy giving this presentation. If you have any questions now, please let me know, and I'll try to answer them.